So in the previous lecture we stopped at this state. So today in this lecture we will be discussing about the degeneracy. So degeneracy means when two or more quanta states have the same energy, it is called degeneracy. So in the last lecture we found out the value of nu j, which is nothing but b j into j plus 1 centimeter inverse, and energy of the lines is nothing but 2p into j plus 1, and the intensity of the lines depends upon the population, and the population is explained by the Maxwell-Boltzmann distribution. Okay, so what I meant to say is that if there are different energy levels and then there's this energy level which has the same energy, so and the intensity of this line depends upon the population. Okay, so these energy states might have the same energy. They are called degenerate states, and the intensity of these lines depends upon the population, which is calculated or determined by the Maxwell-Boltzmann distribution. Okay, that is Nj divided by N naught is equal to e raised to minus del E divided by Kt, where Nj is the population of the jth state, and then if we are taking for degenerate states, this equation modifies into Nj divided by N naught is equal to Gj e raised to minus del E by Kt, where Jg is equal to degeneracy of the jth state. Okay. Since rotational energy state of a molecule are related to angular momentum, we can write Ej to be equal to L square by 2I. We found out this equation in the last lecture here. Okay. Also, L is nothing but root of J into J plus 1 H cross. Okay, since L or J is quantized as H cross, L has both magnitude as well as direction. If you take two molecules and it is rotating about its lab axis, we will take the Z axis as the lab axis, and this one theta. This is the lab axis, that's the axis of rotation, and this component is nothing but the rotation, and this component over here is nothing but the LAZ. And we studied LAZ is nothing but MH cross in our quantum mechanics course, where M is nothing but minus J to plus J. Okay, here LAZ is L cos theta, the cos theta component. We can write LZ to be equal to L cos theta, which is equal to MH cross, and L we know it is nothing but J into J plus 1 H cross, the root of J into J plus 1 H cross cos theta is equal to MJ H cross. This can be written as J MJ. MJ is tending from minus J to plus J. H cross get cancelled. We get the equation cos theta to be equal to MJ divided by root of J into J plus 1. Okay. So let's take an example. We'll first consider we'll take a case where J is equal to 1. So if J is equal to 1, L is nothing but root of H cross root of J into J plus 1 is equal to root 2 H cross, or H cross root 2, and E is at L square by 2I, right? L square by 2I. So H cross square 2 divided by 2I. E is equal to H cross square by I. Okay, and MJ is minus I 0 plus I. Okay, So from this we can draw this diagram. Just two atoms connecting it, and this one over here, the L is nothing but root 2, so you write root 2 here. Also there's a root 2 here because this is from plus 1 0 to minus 1. So this is how the diagram looks like. So Z axis is the reference axis, or we can call it as the molecular axis, and the total number of we can calculate the total states, the degenerate states, that is 2j plus 1. So total degenerate state, two j plus 1 is nothing but 3, which means it's a threefold degenerate. So there are 3 types of alignment. Okay, so these are the 3 orientation. Now we'll take the case for j is equal to 2. I will just write it like this. Okay, j is equal to 2, that means mj is equal to minus 2 minus 1 0 plus 1 plus 2. So let's see its orientation. Also I forgot to mention this one. So with these mj values, it will look like this. This is equal to 0, mj is equal to 0. This is for 1, this is minus 1. Okay, so this is how it looks. For mj is equal to minus 2 minus 1 plus 1 plus 2, it will look like this. So this is for plus 2 plus 1 0 minus 1 and minus 2. Okay, before that let's find few things like L value and all. So L is nothing but h cross root of j into j plus 1, 2 into 3, that is 6. So h cross of 6, so h cross root 6. Okay, so this is the phi orientation. From here we can understand that the angular momentum vector can lie anywhere on the surface of the cone for a particular value of mj. That means the rotational energy depends on the j value, the rotational quantum number, and not on the orientation. Okay, also I forgot to write the total number of states. Total number of states is equal to 2j plus 1 5, that means 5-fold degeneracy. Okay, this is 5-fold degeneracy. I'll write those important points as well here. So now I'm going to draw a diagram which will give you a clear picture of what I was trying to explain all this way. So as I said before, the total degenerate state, the equation is 2j plus 1. Okay, remember this formula. With this equation, I'll try to explain j and the degenerate states. Okay, so if j is equal to 1, j is equal to 0, if j is equal to 0, j is equal to 0, what is gj? G of j is equal to 0, because if you substitute 0 here, it will be 0. So I can draw one line and write if j is equal to 1, it is 0. This is 0. If j is equal to 1, what will be the gj? It will be 3. So I'll draw 3 states. So what does it physically means? It physically means that 3 states have the same, 3 quantum states have the same energy. Okay, so this will be 3. If j is equal to 2, that means it has 5 states. Okay, so this is gj is equal to 5. So in the beginning of the lecture, I set a point. Here it is. So the intensity of the light, intensity of the lines depends on the population. That means higher the population or higher the degenerate states, the intensity will be more. I hope you understood what I was trying to explain before. So that's it for today's video. See you in the next one.